Welcome everyone. I would like to welcome Professor Piotr Homola from Polish Institute of Sciences, from Institute of Nuclear Physics of Polish Academy of Sciences, with a very interesting lecture. I think that you haven't heard of such a correlation. I think it will be a new topic for most of you, and it's really intriguing because it is a research on a correlation between cosmic radiation and between earthquakes. So it's not obvious to think that those two things might be connected, and our professor will tell us more about it. So thank you very much for agreeing to our invitation, and the floor is yours.
Thank you, Gabriela. Thank you for the invitation. It's a pleasure to share with you actually the biggest excitement of my whole career. Well, that sounds heavy, but it is what it is. This slide you see, the starting page is already summarizing the effect. So we have the Earth shaking, actually the whole Earth, not local events, and we have cosmic radiation, these arrows here, and there is some statistically solid connection, correlation, which you can basically click to the article already now. But we do not understand this phenomenon completely, so we have a question mark. I mean the collaboration I coordinate, I work with Cosmic Ray Extremely Distributed Observatory, which is primarily dedicated to cosmic rays, not to earthquakes. Nevertheless, from observing the universe, we got this topic, which is cross-domain, cross-disciplinary topic, and we try to understand. No success so far, so we have only this observation at the moment. We are trying hard to understand what we see, but okay, maybe we need more brains, maybe we need you actually, so I count on you in this talk. I will not only presenting, I will be also asking. Okay, and the thing seems big to me just because we see no causation. There is a correlation, but we actually do not understand how these tiny particles, cosmic rays, could trigger a global seismic phenomenon. So like in this figure, we do not know why the gate was broken. What was the force to break this gate, to create the conditions that the small duck can enter. The small duck is the cosmic radiation, and the gate is the Earth. So no causation. And okay, the problem is unsolved, not yet on this list you see right now. I hope everybody know the list of unsolved problems in physics by heart. If not, I recommend visiting this website. This is because when you see something unexpected, like this phenomenon I'm talking about, then maybe instead of neglecting, ignoring, you might try to connect with the existing issues. And then maybe the chances for more understanding of this world are growing. So the list of unsolved problems in physics, the cosmoseismic effect not yet here. Maybe if you are familiar with Wikipedia edition, you might try to include it. And as I said, the observation comes from contemplating the cosmos. I'm advertising here our greatest laboratory, which provides a lot of signal completely for free. It is actually an ocean of particles. Even very high energetic particles might come from the deepness of the cosmos to enter the atmosphere and generate next generations of secondary particles, which can be observed on Earth with different techniques. But for this talk, we focus on particle counting, maybe tracking. If we have a CCD or CMOS camera, we can have a particle track in this camera. So this plot shows you the illustration of working principle of the largest cosmic ray observatory on Earth, the Piotr Observatory, located in Argentina. Has many detectors, large surface covered, and many particles. So it works like that. And at the end, we have the secondary particles hitting us every second, and it's a lot. It's really an ocean. So why not to study this ocean at a larger scale? Not only individual particles are interesting, and this is the purpose, the main mission of the CRIDO collaboration, Cosmic Ray Extremely Distributed Observatory, where we want to collect all the available radiation data, not necessarily integrate all the existing experiments into just one mission. It's enough to have an alliance of these collaborations. Whenever the data are open, it's already us. And it means including professional detectors like the Piotr, for instance, but also very small, affordable sensors, for instance, smartphones. Here you have the application we are operating, and it works. It provides data with untrained participants, like amateurs. So even I think at the moment that we have installations all over the world, and something like 20 million particle track candidates are collected. So this is a resource, and we hope that this global approach will really reveal a new information about the universe. We are also working internationally, and you have the main article linked here. And this global mission gave us this biggest to date success, which is the observation of a completely unexpected phenomenon, the cosmoseismic correlation. So this is already a discovery, larger than 6 sigma effect. This is a statistically solid thing, and importantly, you see the list of authors here, and not all of them are fully trained physicists. There are amateurs as well. So it already demonstrates that this kind of research might engage really everyone. And now I'm coming to the point, the cosmoseismic stuff, chronologically, because it's partially my personal experience. I will tell you how it started. So it started with a major earthquake in Chile in 2010, devastating thing, a disaster. And the Piotr Observatory is nearby, 500 kilometers away. And at that time, I was a member of this Piotr collaboration, and I was attending a collaboration meeting only 5 days after the earthquake. And we have felt one of the aftershocks. Literally, sitting in the lecture hall, the beamer started to shake. First we laughed, and then we escaped, and oh, okay, nothing serious happened. That was just an aftershock. But somehow it stayed in my memory, and it was particularly interesting that the cosmic radiation detection at that time, at the time of the earthquake, and actually several hours before, showed an anomaly. You see here in blue, and the arrows show the time. Anomaly. So could it be that this is a precursor of an earthquake? If this is a precursor, then could we predict big earthquakes? These kind of questions are immediately on the table. But this particular anomaly, firstly, it was not explained. And secondly, it was not published. And thirdly, it was not studied deeper. So 3 points I should feel really shame, because I was the member of this collaboration. Okay, I was not in the working group which studied the data, but only a few years later, when I was already starting my own collaboration, the CREDO collaboration, I thought, okay, I remember that event. Maybe the global approach could do the job. And I think it's kind of a duty, a scientist's duty, because if we have even a small chance that our data show how to predict earthquakes, then we are obliged to check. So we started this study. And of course, we started with local analysis. So the earthquakes around the Piotr Observatory, mostly in Chile, and the Piotr Observatory data. But it gave us nothing. Only switching to global data set of earthquakes gave us something. And it, of course, included a hypothesis, which you have briefly sketched here. This is based on the mechanism that produces the geomagnetic field, the so-called planetary dynamo model, where you have some complex magnetohydrodynamic behavior inside the Earth, roughly speaking, liquid iron, which might produce in parallel two things: a mechanical impulse, like a water in an aquarium. When it is waving, there is some pressure on the walls. And in parallel, maybe faster, the electromagnetic change. If this liquid iron produces the geomagnetism, then a change inside results in a change of the geomagnetic field around the Earth. And this means that cosmic radiation immediately feels this, and detectors on the ground could show a precursor if this electromagnetic change propagates faster than mechanical impulse. So this was the hope. I can already tell you that it didn't work, but we had something. We took the public data, the Piotr data you see in red. It's only a small fraction of time. The Piotr started data taking in 2005. But we have other stations. Here you see a Russian station in green, and in Finland, in Oulu, we also have a station. These two are parts of the European, not European, it's a neutron monitor database. It's a global network of cosmic radiation detectors. You only see two here. There are more, many more, something like 40, 50 detectors. You also see earthquakes. Everything here is binned in 5-day bins. Don't ask me why, because I don't understand why this is exactly 5 days. And for comparison, you have the yellow color showing solar activity. So you can see that immediately that the cosmic radiation is anti-correlated with the solar activity. The more activity in the sun, the more plasma around, and the cosmic particles have more difficulties in reaching Earth. So that's why the flux gets lower. But you do not see, but at least not by eye, at least not me for sure, any correlation with earthquakes. Maybe some trend here. Okay, there is a step around 1972, but this is a technical step. It's a very narrowly located in time change of the precision of the seismic network of detectors. But also you see some increase here, and it might also be the continuous growth of the number of detectors. Important thing, we speak about large earthquakes here. Large means the magnitude larger or equal, or maybe only larger than 4. 4, remember that name. And all the data is public, so you can immediately try yourself. Even now, you can do the script, you can repeat this plot, you can repeat all the effects, because all is described in the article. Okay, so this is only to see, to taste the data sets. And now, to be more specific, the cosmic radiation. What do we observe? What is our observable? So here you see a sample signal. At the beginning of 2014, you have this 5-day binning, and each 5 days contains 5 peaks because there is some daily behavior also not fully understood. And what we take for our study, it's a part of prescription, but again, it sounds like a magical formula, magical way of doing science. But please let me explain why. So we take the average for these 5 days, and we compare with the average on the other day. So this is the change in average cosmic radiation flux. Why this kind of observable? This is motivated by our hypothesis. It's that these changes of the geomagnetic field resulted from changes in planetary dynamo might not necessarily give a direct increase or decrease. It's not obvious what would be a result of a very complicated behavior driven by magnetohydrodynamics. So we only want to check the change of behavior, so to say. It doesn't matter which way, the absolute value. Does the flux change or not? So here you see at the bottom on the right, we take this change with absolute values. An example only here, 15 days of the data. Then we take the earthquake data, but for the earthquakes we take all the planet, while before we only take one site, one specific site. And we compare this local cosmic radiation with a global seismic activity. Again, you have an example here for just one beam. You see the blue points, the first 5 days of the year 2014, and the rest is what happens within a decade. So you see that within these 5 days, basically, and in the wider time window, the earthquakes are distributed actually according to the tectonic plates positions, and on the borders between these plates we see earthquakes mostly, not just one point, not just one location, everywhere. This is important, a global feature. And now the prescription. So I will spend a while on this because I would like you to understand all the details. Maybe you will point out to some problems in this, and then we can together find out some new ideas. So we have two data sets: cosmic rays measured local and earthquakes measured globally. We divide all the data into bins, 5-day binning. Then we shift the earthquake data 15 days forward. That's magic, really. And we have a big time window, 5.4 years, 4.5 years, or 9 years. So it means many hundreds of bins. And we compare the pairs. So this is why I call it a dichotomic correlation. It's like throwing coins. You can imagine throwing coins literally. Here is one person who is throwing, here is another. If these data sets are independent, there should be, on average, the same number of pairs of each type. Head, head, tail, tail, head, tail, tail, head. So we want to measure this. Is it distributed as we expect from independent distributions or not? So for this, we find the medians in each data set, which gives us roughly half values below and half above the median in each set, and we compare. So at the end, it gives us a chance probability for some imbalance here. If everything is as expected, chance probability will not be small. Okay, so now the same, but in an even simpler way. So a median for each data set, then half of the values below, half above. Okay, and a comparison. But this comparison is only made after we shift one data set forward. In particular, we shift earthquake data set forward. So we have matching or not matching pairs. Matching means that the color is the same. Not matching is not the same. Like with coins. And yes, and we have imbalance, as you can already suspect. We have imbalance, which is the cosmoseismic correlation. Very unlikely. And you can see how it looks with the data. You have evolution in time, and each point corresponds to the past 4.5 years. On a burning sample, this is a burning sample with not only the Pierre data, in addition, we also check the other two sites. And as you can see, only at some point in time, we begin to see the effect. In the three sites, basically at the same time, not exactly at the same, but similar time. We also see that the effect occurs rather after the solar maximum. Okay, so that's the first feature. Evolution in time, not always present. The effect is not always present. The next feature is this shift in time. The shift only when we shift the earthquake data in time, 15 days forward, we see the effect. Only one side shift gives that. The other side, nothing. So it could be a precursor. Could it be a precursor? Looks like that. But why? And what actually drives this? The other a very peculiar feature is the regularity of the evolution in time. So here you see the final calculation, which gives the 6 sigma, where the burning sample in gray is disregarded from the analysis. And in the past, applying the prescription which was performed for the burning sample only, we apply this prescription and we get 4 more peaks, or maybe it's not peaks, dips in chance probability. So this correlations reoccurs in the past with some period, which is not, maybe it's close to solar cycle, but it's not exactly the solar cycle. And as previously mentioned, the dip in chance probability does not correspond to the maximum solar activity. So it looks like something solar, but not necessarily connected. Okay, so this is the end of the article. Now, what do we do to understand the feature, the phenomenon? For this, I need to tell you about one more property, which is small scale sensitivity to the starting time. If you change the starting time only by a very small fraction of time, I do not mean the shift. This is changing the starting time, T0, where you start to count the beans. So it shouldn't matter, right? At least this is what we would expect. This T0, if changed, could remove the effect completely. So this might be an artifact. Of course, you would suggest so immediately, and this is also my first thought. But many groups did it independently. I did it myself many times, and the effect stays there. So if this is not an artifact, okay, it's not closed. You can try yourself. You can try yourself. But if we assume it's not an artifact, could it give us some physics hints That's the point I have for you today. So to check, one of the cross checks is a very small stepping in T0 to see what is the resultant imbalance of this matching and non-matching pairs. So n plus is matching, n minus is not matching. So here we have the step 1 hour, and you have some bands of imbalance. In this time, on the right, you see that there is a peak. The imbalance has its maximum, and it's 10 to minus 14. It's just an example for one side with slightly changed bin size. But you see that this imbalance is even larger than demonstrated before. We had 10 to minus 10 at best for the Auger data. Here we have 4 orders of magnitude less. And see the shape in zoom. This is the thing I want to demonstrate in very detail. So here you have a fragment of the data at the location of the peak, and you see that if you shift T0 by 5 days exactly, nothing happens. So these shapes are very similar if you shift by T0 equal 5 days or multiplicity. Why? Because then you change only one beam. And if you count n pluses and n minuses, there could be only a small change, 1 plus minus 1 with the shift by 5. But if your shift is smaller, dramatic things can happen. In particular, you can lose 50 n pluses from maximum to minimum, 50. So remember, we have very wide time window, and we shift here by 1 day only, and we lose immediately 50 bins, which removes the chance probability completely. If you zoom even deeper, you see that a shift of the order of minutes already does something, minutes. And this is intriguing because our cosmic ray data used here are binned with 6 hours binning, 6 hours. So a shift of the order of minutes should not affect very much the 6-hour binnings. The other thing is with earthquakes, where we have timestamps of each event. So every second might matter. So this plot directs us to earthquakes. One more thing about the sensitivity of T0 is that it is not the same location of the maximum at each time. So here you have a comparison with another decade. 8 years earlier, the position of the peak is elsewhere. So it is evolving. It is evolving in time. Could it be physics? Please consider the following toy model. So if we have a specific signal, not fully regular, so not every period the same, like here you have a peak and four bins later another peak, and then 2 bins later another peak. What can happen? I will do this animation for you. So one position, you have 3 coinciding bins. But if you change T0, I mean the dashed line symbolizes the borders of the bins. And if you change this T0, the starting point only slightly, you might lose this coincidence in many places. So this could be physics. Okay, we are not completely sure if it is not artifact, but at least we can point to some physics model, even if it is ideal realization, that could do this kind of behavior. Okay, and to go further, you might just take it as a definition, or you might ignore. I will just explain that I will be using stacked graphs, which is accumulation of earthquake number at a certain part of the period which is being investigated. So for instance, if I want to check for this kind of behavior, where I want this regularity, but not necessarily the same phases of the peaks, one of the way is to do this stacked cumulated graphs. So for instance, if I have to check 1 day, average 1 day, and my binning is 4 hours, I will start from midnight, and my first bin will be 0 to 4, and I will take the number of earthquakes in this particular bin every day. Then if I want the sliding to see the trends better, I can repeat this thing for a slightly changed beginning of the border. So I can start at 0.1 or 0.01, whatever the step. So I accumulate the data in the period being investigated, just to see whether my signal, if accumulated, is flat or maybe it shows some features. And here is the daily plot. It's already striking. So not flat. First conclusion, not flat. We do the accumulation, as I said, in 4-hour binning, and we do the sliding step of 10 seconds here. Okay, maybe in this case it's 1 hour binning and the step is 10 seconds. Also, the wide window is 2000 days. So it's slightly different than before. The beginning of the period is 2014. So you see some features like the safest time of the day, like this maximum at 0 UTC. It's super strange, not what you expect. 24 hours. 24 hours. You can also see the evolution of time, the evolution in time of this particular shape. When you compare, for instance, the peak at 7 p.m., something like here, with the minimum. And you see that this evolution has a period where it goes really dramatically up. So this 5 years is dramatic. It creates basically the whole effect. So again, this temporal factor, the evolution in time. And you see that different features might evolve differently. This is one particular pair of bins, and this is another pair of bins. Here the evolution starts earlier. So the picture is not steady. And it is even more intriguing if you switch to 7 days. 7 days. It's another number which sounds anthropogenic. 7 days gives even sharper asymmetry. Here you see the picture for 4-hour binnings, 60-second step, and the window is wider, 4,000 days. So please note this maximum at Sundays, 1 to 5 p.m. 24 hours later, another maximum on Monday, then on Tuesday. And on Saturday, the same time, you have the minimum. And on Friday, the same time, you have the minimum. So you immediately see that the previous picture must be a composition of this weekly pattern. So must be less clear, just because you see that the days are different. The days of the week are different. When you see the zoom here on the right, you see a very characteristic signal, like our ideal toy model shown before. So don't even have a name for this. I call it Zorro signal. So it is very sharp, just because we take this 4 hours. Somehow this 4 hours is meaningful. I will show another slide to explain. But here, please note on the right at the bottom, you also see the evolution. The evolution which begins not long time ago, a decade ago, and it gets dramatically up during this 10 years. So this picture is not, again, it's not steady in time. It is just one decade. Okay, and if you change the binning, you see the plateaus. In the minima or maxima, you see plateaus. So you compare the 4 hours in black with 15 minutes in red. So you see the sharpness only when you use 4 hours. So for some reason, this 4 hours is meaningful. And even stranger behavior is that sharpness of 7-day periodicity, sharpness which you can see here. So you check different periods with a step of 1 minute. So 10,080 is exactly 7 days. And if you change this period only by 1 minute, you already get a dramatic drop, and several minutes brings you to the ground, basically. So perfect 7 days. Perfect 7 days. And before we have seen 24 hours, but this 24 hours, to my understanding right now, is related to the 7-day behavior, just because in the 7-day pattern, all the days are different. There is some literature on these two periods. Here you see a very strong statement about 24 periodicity, and the authors call it a new window to explore the physical mechanism of earthquakes. So why it is strange? Just because it dominates and there is no lunar period. Why lunar? Because you expect tidal forces from the moon, like in oceans. Moon has a larger gravitational impact on Earth, so you would expect this lunar period, lunar day, which is 24 plus 50 minutes, 24 hours plus 50 minutes, to dominate in the earthquake data. But it is not dominating. It is not even visible. On the other hand, the 24-hour period dominates. Another article with the United States data, where they see both 7 days and 1 day, and they conclude it's anthropogenic because no other processes that give 1 day and 7 days are known in physics. So anthropogenic for sure, according to the authors. But we can do a check, actually not just one. There is a database of the human-induced earthquakes. Many sites across the globe are producing artificial earthquakes. These are different processes, including fracking, mining, nuclear explosions, many processes, many sites. This number gives you the sites. In each site, you can have many earthquakes. So what we can do, we can extract the sites, the known sites where the human efforts could generate earthquakes, and we can find our weekly pattern then. And you see a comparison here. We have extracted these artificial sites with a ridiculously large margin of plus minus 5 degrees, which is already thousands of kilometers, a square of 1,000 kilometers. So you do not expect, where there is a mining effect, you do not expect an earthquake 1,000 kilometers away. You expect an earthquake at the location of the mine. But here, to be on a super safe site, we've extracted even more. And you basically see no change in the shape. No change in the shape. So we do not think it's a human effect. We have done a similar test with simply a population. Maybe people are wake up at the same time and they generate something. So we have extracted from the data the most populated countries: China, India, States, Japan, where more earthquakes occur, and nothing. The shape stays there. So we do not see it's anthropogenic. But we see this periodicity very clearly, the 7 days. And it seems like large fraction of earthquakes is induced by something unknown. Maybe it is an explanation of our cosmoseismic phenomenon, but then what could be the physics behind? This is only a technical thing. The more exciting question is what is behind. And okay, now I will wait for your ideas. But really, my impression, my excitement is that there might be really a big fish just around the corner, and we don't know what to do, what to do with this. Okay, we have ideas, we try our best, but maybe we need your help, and you are invited. Okay, thank you very much, and now I hope for some questions and ideas.
Okay, so there is a first question in the chat that has been partially answered, but still I think we can consider this question because one of the participants asks, is there an influence of the radiation particles on the Earth magnetic field, or is there any other reason? I know that during the lecture there was a slide that about that we don't have a causation, but still, can this be some new physics potentially?
Potentially, yes. It's like in Sherlock Holmes. If you eliminate all the things, then the rest, even if it is really unlikely, must be the truth. So yes, we do not see causation. We do not even imagine how cosmic rays could trigger a global effect on earthquakes with magnitude larger than 4. Okay, there are some ideas that even a tiny impact might trigger earthquakes in the locations where they are nearly ready. But this would require local behavior, and we do not see a local behavior. We see a global effect, and that's the point, that even if cosmic rays measured locally might have some impact on, I don't know, on temperature, on pressure. First of all, there is a big problem with magnitudes. This pressure change is really tiny, and there are much bigger pressures needed to do anything in geophysics. But even if we assume that something happens, maybe it's nonlinear, whatever, then no idea, at least in my mind, how it could trigger a global effect. So in many places. So what is the way you're asking the questions? Through chat only, or you can speak as well? I see an interesting question. So dark matter.
I mean, I could ask the question, but I'm in a train right now, so I would prefer to use chat, unfortunately. I can turn on the camera for a second so you can see me. Hello. Nice to meet you.
Have a nice trip.
Thank you.
So did I answer? Have I answered your question?
Yes. Also, I wanted to ask about this dark matter question.
So that's actually the leading hypothesis. That's the leading hypothesis. This third factor in the play might be a dark matter stream. And then we can expect that it drives both cosmic radiation and earthquakes. And what we see as the cosmoseismic correlation is only a secondary effect. It's like in the second slide when we have a gate which is broken by something and a duct. So duct is not connected with breaking the gate, but it enters the gate because the gate is broken. So dark matter is tempting. the massive bodies should play roles. So there is an intrinsic dynamics in this, because planets are moving. We are moving around the sun. There are different positions. Moon could play a role. If you check the backup, there is a literature where it is demonstrated then that there might be a magnification, amplification of the stream of the order of even 7 orders of magnitude through a gravitational lensing by a planet. 7 orders. So that's something. The point is that if there is a stream, we could observe a specific periodicities in the data. So for instance, I have spent a lot of time to look for a sidereal day periodicity, which is the period of rotation of Earth with respect to the stars. It is 24 hours minus 236 seconds, nearly 4 minutes. So this could indicate the presence of such a period, could indicate that there is some direction which is somehow distinguished, some special direction, and the Earth, when it faces this particular direction, it might suffer. Okay, and you find this slide in the backup as well. There is such a line, but it is not stable in time, as everything here actually. So in the decade I have mentioned, 2014 to now, there is such a line. If you want, I can show you. Maybe I will open the show again. Sorry for jumping. Here is the slide where you see that the sidereal day periodicity is seen both in this DNCR change and earthquake sum. You see the panel on the left, the domination of the 24 period. One here is 1 day. Both data sets have this dominating 24. And here on the left, you have in the 2 data sets something very close to the sidereal day period. In the earthquake data is actually practically at the point. Maybe the cosmic rays are somehow shifted, but it's all white, so maybe it's uncertainty. But it's not that simple. You have other lines, and what do they mean? You have the change in time, and what does it mean? So yes, I can confirm that the dark matter stream hypothesis, at least to me, is the leading one. Not my idea.
Yeah.
Not my idea. It's an idea of other colleagues who were listening to the presentation like you do right now, and they thought, okay, maybe it's dark matter. Okay, let's try.
I mean, it's also like some kind of body that it's everywhere, so it could actually like have a global effect on the whole planet. So I suppose that's also the reason why it could lead such a role.
So yes, that's it's all okay. You are right, but there are problems in the data analysis, and one of the features we would expect if it is a stream would be the behavior of this, I can say, annual behavior of the effect, or these evolutions, but we don't see this. So I have demonstrated the asymmetry in the weekly pattern and its evolution in time, and it's quite monotonic. It's not yearly, and we have this dominating 24, or rather 7. So think about it. What is this exactness? 7 days or 1 day, if you prefer. What could produce this? Two ideas immediately come to one's mind. One is gravity. Okay, 24 points to the sun. That's clear, because this is the rotation of the Earth with respect to the sun. Full rotation, 24, period, 0. Not less, not more, 24. And the gravity, because of course Earth is non-uniform. That's some part of the mass might be might be closer to the sun, some might be further away. So the same position of this mass is reached every 24 hours, the same position with respect to the sun. But the sun gives a weaker impact in terms of gravity of its own than the moon. And we do not have a lunar period. So that's one argument against gravitational effect. And the other is the dynamics. The gravity does not change decade to decade. Maybe million years is the scale that you can see the continents moving. Millions of years. But not decade to decade. And we have this kind of dynamics. Okay, so if not gravity, then what? What else? The magnetic field is another environment which is driven by the sun, and where the full rotation means coming back to the same conditions every 24 hours on average, but not necessarily the same day to day. So this is at least qualitatively similar to the behavior of the seismic data. That I've demonstrated a weekly pattern, but it's not like every week is the same. Just the opposite. You only see the effect when you accumulate the data over a wide period. If you check individual weeks, they do not show the similarity or very weakly to the global pattern. So if I may, the other, I have this is one of the first backups. Yes, this one. So this is a candidate, geomagnetosphere. We have some data, we have satellites, and as I said, the full rotation means that the field of the geomagnetic field vector returns to the same on average position. So you have the sun on the right, and you have features here. You have these wings here. Roughly, maybe the distance in time between these two wings is 8 hours. So maybe it is something related with the two consecutive maxima in the weekly pattern plot. So this is a wide topic to study, and it gives surprising effects, which you can see here. It gives the difference between Saturdays and Sundays. So it's not true that we do not have the 7-day features in nature. This is even if you don't believe in earthquakes that they give 7 days. Another thing is here, the qualitative difference, that on Sundays the same time you have the minimum, and on Saturday maximum. So it's not that, okay, what is the observable? I should tell what is the observable. It is the BZ component of the geomagnetic field, not geomagnetic, the magnetic field in the geomagnetosphere. BZ, which is perpendicular to the plane you see. And you might simply sum up this BZ values in bins, like we did with stacking earthquakes, and you get this. The problem is that you do not see the other days. So Mondays are not there, Tuesdays are not there. So that's not super easy. Here you see the literature on lensing dark matter. If you want, you can read. Okay, I hope it answers partially, but the answer is clear.
Yes, thank you very much.
We do not know. Please come help.
Okay, I will.
I see Valerie is raising hand.
Yes, thank you. I hope you can hear me properly. Greetings from Düsseldorf. And thank you for your really fascinating insight into your research. It sounds like you have exciting discoveries ahead of you. As I'm new to this field of research, I was wondering, since you're doing research on quite a big scale, I mean, this is not just mixing some solutions in a jar like we chemists do. How do you make up for not having, okay, you do, observe something, you analyze it, but you cannot recreate it, because that's our approach of making science. We always look for, okay, can we recreate it? And then we have our proof, okay, this is connected by causality. How would you, or how do you make up for this? Or maybe I'm wrong.
So not sure if I understand exactly what is your question. So I will try to tell you a few things actually about this particular phenomenon. So first of all, it is unexpected. It is not what we wanted to see. It's not a scenario we are trying to verify. Maybe most of scientists are doing their science that way, that they have some hypotheses, they try to verify it. So okay, we did have a hypothesis, but okay, maybe we did not even disproved it, but we saw something completely unexpected, and I mean here this regularity of the effect in time. So when I was looking for this correlation after this first inspiration from the anomaly in 2010, I was sure that I'm looking for something steady in time. And of course, if the mechanism is driven by the Earth interior, this is the reasonable expectation that there are not known processes inside Earth which are so regular. So we do not know about regularity of a higher order in earthquakes. So earthquakes are basically happening all the time. So it's not like you have earthquakes only once per 10 years. You have them all the time. So it's in this sense, it is super surprising that you check only part of the data and you have the effect, and the other part you do not. And how to deal with this? One way is to first to be sure that you see a real effect. So that's why we have published the finding despite having no interpretation really. And the method, maybe it's not from a book, but it's super clear, super easy. It's a throwing coins is something you can imagine actually from the preschool. Throwing coins, and you can do the throwing coins experiments, and you can check your imbalance. So that's the first thing, to have something solid. We okay, maybe there is a number of magical parameters like the beam size, like the magnitude threshold, and so on and so on. This shift, 15 days shift. Okay, there was a lot of manipulation, but it was a manipulation on the burning sample only. And then when I removed the burning sample, the biggest surprise came when I have seen the reoccurrence of the feature. every 10 years, basically. That was the most surprising thing, because it's then maybe the sun somehow. It's very close to the sun. Also, there is some possible relation with the moon, if you consider a perigee point where the new or full moon coincides with the apogee or perigee points. So that still, this is all speculations. And now the next steps. Having this steady point, one by one, we want and we can try to manipulate these parameters and check what happens. Like this T0 manipulation, which now seems to be the hint. It has been confirmed many times, and it gives dramatic changes, which are possible only for a specific signal. And we see this signal in earthquakes. Maybe we could demonstrate it. Maybe it will be our next publication, this weekly pattern. To my knowledge, it is completely unknown. We now communicate, collaborate with a geophysicist, which is an advantage, because another thing is that it's a very interdisciplinary subject. I have a very limited expertise, and we have many people in the collaboration, but these are basically cosmic ray people, and we need solar physics, we need interplanetary medium physics, we need geophysics, we need maybe geomagneto-hydrodynamics. Many disciplines are needed for this, and the hope is that when we publish something which cannot be questioned, even if we don't understand the effect, maybe people will start thinking, and this is also the encouragement for everybody, for you, for all of you.
Sounds like it's worth staying tuned for your coming works. Thank you.
Yes, but also you do not need to only stay tuned. You can really do it yourself. You can very quickly write a script, or you can take the existing scripts, then try yourself. That's the best way to feel the strangeness, so to say. Like this geophysicist, he actually was very skeptical about this pattern, and only after he tried himself, then he confirmed, okay, it's real, but it's out of the paradigm. No books will tell you about this. The 7-day pattern seems to be real, but it's not understood. So maybe it is a gate to something really exciting.
And I also have a question. Is it possible to look for a similar correlation on other planets? So is it possible to see if there are like Mars quakes, Venus quakes, etc.? And
yes,
for example, have detectors there.
Mars quakes are collected. It's the database is even open. Maybe you can quickly Google out Mars quakes data download. Not so long periods, but you can even find recently, literally a few days ago, there was a news that people were very surprised to see a seasonal behavior of Mars quakes. Seasonal means that in the summer, Martian summer, it's new scientists. Maybe you can find a link and paste on the chat. New scientists, the article there, and Mars quakes. It should work. You see, 2 seasons only, so not long period, but you see this what is expected for a dark matter stream. That on one side of the sun, you have an increase, on the other you don't. Okay, it is not super similar to what we see on Earth, and I'm not even sure if it is one story. But if we speak about observations which are unexplained, then maybe this is something. Another thing you might consider, it is on the list of unsolved issues, flyby anomaly. Have you heard about it? Flyby anomaly. Who heard about it? You see, that might be the point I've made at the beginning, that knowing the list might help. Then you might connect the puzzles. So flyby anomaly, you can find in the list of unsolved problems in physics, is anomaly of the flight time of spaceships, satellites, which happens not regularly. Sometimes it happens, sometimes it doesn't, near the planets, and no one knows what it is. Okay, we are pretty confident about Einstein's theory, but in this case, it's not always working. So one of the hypotheses is dark matter. You can find the article in the references, flyby anomaly references. You find dark matter article. Not conclusive, but still, if we have a collection of pieces which might not immediately be considered connected, your mind is already working, and you might at some point you might find the connections. So flyby's anomaly, of course, if there is something more, not only planets, then it would induce these anomalies, because you need to know all the ingredients to calculate the flight time. And it might happen sometimes only because these amplifications are not steady in time. As the planets moves, as planets move, the amplification region changes its position. So at some position there might be a flight anomaly in the year 2015, and the year later it might disappear. Flies by anomaly. maybe you will find more such peculiar. There's something is about Saturn also. Some seasonal behavior of Saturn, not earthquakes. So instead of giving answers, I'm only producing more and more questions. Sorry.
Interesting tropes. And what would be your advice, like, to young scientists, to students who would like to join this kind of research? Like, what skills would they need to work on?
No big skills are required, actually. It's really zero level. So if you, maybe Python is helpful. But you know, Gabriela, you did the practice with me, right? So
yes,
it's super easy. And you just come, and then we think what to do. There are many ideas. I always count on creativity of the participants, that we do not know a priori what will work and what will not. We do not have a priority knowledge about this. There are no experts in this. I'm not an expert in this. So if you have an idea, maybe this is the best direction, because it is your own idea and you have the motivation to follow it. If you have the idea from elsewhere, from me or from your colleague, then you are like a soldier. You just produce an outcome as required. But if it is in your own mind, your own curiosity is most precious thing. And that's the best advice. Follow your own curiosity. Try to have questions. Try to answer these questions with the means you have, like Marsquakes. This is something that could be done immediately, basically. And consult. Of course, do not work alone. That's why we have a collaboration. That's why we try to spread the word. You might see actually the press release on the cosmoseismic effect. It went to media worldwide, was accepted very nicely. It's biggest websites and journals gave it really a place, but practically zero impact in the scientific community. And maybe I understand why, because it is too intriguing to dedicate time. Many colleagues say simply, we do not believe such a connection even exists. So if there is no time to convince, if there is no time for them to check individually, they might give up, and because they don't believe. So if you feel like intrigued, maybe the best way is to try to do some exercise on your own, then consult. You might contact me. You are all welcome to write me. And who knows, maybe you will be the key author of the next discovery paper.
Thank you so much. Thank you for joining us today for this very inspiring lecture. And for others who are listening, I must say that practicing internship with professor was a fascinating experience, and I really recommend it if somebody is looking still for summer practice, summer internship, or something like that. So thank you so much for your time. And
Thank you.
thank you.
Bye-bye.
Goodbye.